Hello, I'd like to welcome everyone to the Debottlenecking Blending Processes Tech Talk. My name is Crystal Futter, and I'm the Marketing Communications Manager for Energy Industries Business in Canada, and will be the moderator for today's presentation. Due to the number of attendees, everyone's microphones have been muted. However, if you have a question for Pablo, I encourage you to enter it in the Q&A box that you see on the right of your screen. Please note that our presenter is sharing information today, and the slides you're about to see are subject to change. ABB does not assume responsibility for any errors or consequential damages to software or hardware described in today's presentation. And without any further ado, I'd like to turn time over to Pablo Garcia, Head of Strategy and Business Development for the Cellier activity at ABB.
Thank you, Crystal. Well, welcome everyone. Today we're going to be focusing on one of the series of technological developments that we've been working on. This is intended to be the first of a series of presentation in which we not only analyze some technological developments, but we'll focus on how the technological developments affect investment, return of investment, productivity, the rate of return. Today, again, we're going to be focusing in the first one of a series, the drum decanting unit. Typically, we have focused on the savings produced by a drum decanter. So we have traditionally looked at how good the machine can decant the drum components, what's the cycle time, what's the residual quantity left inside a drum after we rinse it. We have tilt the drum and we can rinse it, heat the basil around it, and then flush and rinse the component. What we're trying to do is, besides the characteristics that I'm not going to be focusing on too much on the characteristics of the drum decanter, I'm going to look at how does the drum decanter fit into the overall productivity of a plant. And we're going to take the example of a typical lubricating oil blending plant. In this case, I want you to remember these three numbers because we're going to analyze the functionality in the plant and look at these key value propositions of the technology that we're bringing. So we take a sample of a typical lubricating oil blending plant. This is not based on any particular plant. It's just based on what in general is a lubricating oil blending plant. If we have a 12 million gallon a year lubricating oil blending plant facility, usually 85 to 87, and sometimes depending on the formulation, percentage of that 12 million gallons is base oils, which represents about 10 million gallons, which represents about 1,700 trucks, loads of product are coming into the facility. Usually the bulk components, the ones that are dosed in quantities sufficient to be worthwhile bringing it in bulk containers, in truckloads or isotainers, they're usually about, depending on formula, it may be 8, maybe 12 minutes, but on average, we talk about 13.5% of the total volume, or equivalent to 1.5 million gallons, 1.4 to be more specific, million gallons, or 240 trucks are bulk components, additives that we're adding to the formulation. And then there's a 1.5% of drum additives. Why do we use drums? Well, because it doesn't work putting a dedicated truck if we're going to use the 23,000 liters, 6,000 gallons in a year. We're not going to actually bring a truckload in order to be able to do that. We bring it in drums. It makes economic sense and it makes manageable. These components are in small percentage, but they're the number of different components is much bigger, and the application to or percentage of dosing that we have to do for each formulation is different. So you always see that there's factor that it makes economic sense to buy them in drums. Not the most cost effective from the point of view of the cost per gallon, but it does from the overall cost of capital investment, not buy a truck that I'm not going to use in the entire year. But when we look at these percentages, and here we're looking at volumes driven by formulation. But when we see how we utilize the time in order to dose these components, so the 10 million gallons, you usually pump it at least 200 GPM. So assuming that we take about in the neighborhood of 2,000 hours a year to produce these 12 million gallons, about 30% of our time, 31%, or 654 hours, are dedicated to pump the base oil. Because typically we pump it at 200 GPM. The additives, the combination of aggregate dosing, some of them are viscous, and we don't have to pump that much. We typically pump it at 50 GPM. We're dosing into the operation. So we dilute this bulk component into the base oil. So we pump it at, in average, let's say 50 GPM, which represents that is about 19% of the hours spent in the processing a year, or 415 hours are dedicated to dosing bulk components. And here's the big change: the 180,000 gallons of the 3,000 plus drums that we use a year for the 1.5% drum components take 50% of our time because of the slow pace at which we're able to dose the components. It takes about 1,000 hours, so 50% of the time we're dosing. It's a very slow process. No matter what you use, you may be tilting the drum, you may be decanting it with a hose from a pump, or you may be having to deal with high viscosity products. So in general, there's a significant time allocated to the dosing. It's the smallest percentage of all, but in general, that this is what it constitutes the bottleneck of the facility. The facility can run as fast as the slowest moving component, and the slowest moving component in any lubricating oil blending plant is the drum components. So what we work with is how to, if this is the biggest pain, if this is the biggest bottleneck, and this is what's holding the facility behind, we've been working on a technology that will alleviate not only the savings of, okay, the residual quantities in the drums are 3,000 drums, and if I leave a quarter of a gallon on each, or 0.4 of a gallon in each drum times 3,000 drums, how much um, product have I left inside the drum? Or a manual dosing. No operator in the world wants to be called because they underdose something. So if he's tilting a drum to dose a component, he will put a little bit more just in case. So besides analyzing those things, we want to analyze it from the point of view of how does this impact productivity. So we have this new drum decanter. The drum decanter changes the speed at which we dose. It changes the speed in several ways. First, it actually pumps faster. It has a special pump that actually moves with the lens and can suck the product out of the drum much faster. You can even the more a 20,000 centistone component, very viscous. We're talking about something like cold honey that barely moves. The machine can still decant a full drum in 9 minutes. If you were doing any other system, it would take you between 45 minutes to an hour to decant it. So if you multiply that times the 3,000 drums that you're moving, the significant speed compared to the traditional system makes the entire uh, equation of time change. You cut the hours in half, literally, to decant and push through your biggest bottleneck. We went from 1,000 hours to 500 hours in decanting the same volume. We have not changed the volumes here. The percentages, of course, change because the relative value of we have suddenly 500 hours extra that we're not allocating to decanting the components. So we reduce overall 500 hours and we change the percentages, but that means that we free up time. We got more time to do more things. Of course, uh, yes, we have improved the efficiency of the system, not only on speed, we have also improved in the fact that if I can decant something that is 20,000 centistokes before, in order to speed up the process, those 1,000 hours I wanted to reduce them, I typically would put the drum in an oven. And the proper procedure to put it in the oven is to put it for about 10 hours because the heat transfer coefficient of the drum is very slow. I need to heat it only on the outside. I should not burn the physical properties of that component. So it's a very slow process of heating the drum in order to reduce the viscosity. If we can decant at 20,000 centistokes, suddenly I don't need to put anything in the oven. I can take it from the warehouse directly to the drum decanting machine and decant 20,000 centistokes without being concerned about the 10 hours or that being concerned that if tomorrow I have to do this component or I have to use it for a certain formulation the day before, I have to have it in the oven because it's going to take me 10 hours to heat it up. If I forgot to put it, then that product cannot be done today. But the overall equation is not how good the machine it is what do we do with this extra 500 hours? And for this extra 500 hours, literally, we can push more products through. We don't have a limitation on the 200 GPM basal pumps. We can still pump more. We can still, with a 50 GPM pump on the bulk additives, we can still pump more. And with a drum decanter that can decant in 9 minutes, 20,000 centistokes, those extra 500 hours means that instead of 3,200 drums with the with a drum decanter, I can push 4,000 drums. And overall, what I'm saying is we can go from 12 to 15 million gallons, so a 3 million gallon increase throughput in the system just because we have debottleneck the main component that was pushing drum additives because they're slow movers and the slow moving and the dosing makes them the bottleneck. When debottleneck, then we have even this is a mathematical approximation. I even got still another 180 hours extra. I didn't want to do up to zero, but you get the overall idea that what we're trying to do here is not just saving on how efficiently we can decant a drum, but saving in the overall productivity. So when we go into analyzing the return of investment, we look at it in the as a function of not only what do we save, but also how this um, faster machine that is efficient and saves also contributes to speed up the process. And then I can, without changing the rest of the infrastructure, I can increase my productivity. You can do it probably on a peak because, of course, you make 3 more million gallons a year. Well, you're probably going to need more warehouse, more storage capacity. So uh, not that you don't have to change anything, but it gives you your bottleneck more flexibility to be able to decide if you wanted to increase your capacity. It gives you the tools for increased productivity. So at the beginning, we were talking about the 20,000 we refer to the 20,000 centistokes. In a typical drum decanter, if you tilt a drum by hand or you put a hose, it will top off more or less at 1,500 centistokes. So probably in order of magnitude, 10 times less viscosity can be decanted. Otherwise, you have to put it on the oven because it doesn't flow. The drum decanter that we're talking about can decant 20,000 centistokes, and it can do it in 9 minutes. That's the characteristic that we were talking about. Remember the 20,000. What is the 20,000? Well, the 20,000 centistokes that suddenly are not longer a problem. You can handle those viscosities and even higher, but that's the point of reference that we're using, 9 minutes to 20,000 centistokes. Then we debottleneck the plant. So we talked about 25%. What 25%? What 25% increased productivity? Why? Because I'm releasing and debottlenecking the slowest moving component. I'm suddenly moving it faster, so I can increase my productivity. If I can increase my productivity, I can increase my output with the same blenders that I have. I can produce more because they're not waiting on the drum components. So I can increase by about 3 million gallons, which we can then turn into doing the next step, analyzing how much money is that. So what's my net productivity? What's my uh, gross margin on my current products? And what's going to be my gross margin on 3 more million gallons? It's not a linear calculation because if you're making 12 million today, you're making 12 million considering that you're using 1,000 hours to decant your components. You're going to be making 15 millions and you're not going to be using the same amount of hours. You're going to be using less hours. If you use less hours, then your cost per ton has gone down. So it's not only that you're going to be making 3 more million gallons, you're going to be making 3 more million gallons at a lower cost per ton. So there's a double factor on how you calculate the return of investment because you can analyze, assuming that if I take it linear to what today's productivity is, what is my gross margin on the 12 million gallons that I produce today, I calculate a linear, assuming that everything's the same. I just increase my volume. But in reality, what's happening is I can increase by 25% my productivity, but I'm also reducing my cost per ton because I'm using less hours because we just said 9 minutes to do something that you typically would spend 1 hour to between 45 minutes to an hour. So my labor cost per ton has gone down. Also, because I don't use an oven, my kilowatt per ton has gone down. So this is a general idea. We're not going to go into the details because every manufacturing facility is different and will have a different equation of how this is affected, how much you pay per hour of labor, how much you pay per kilowatt. So I can assume, yeah, 15 cents per kilowatt. Well, we can go into details on every facility and analyze the return of investment. That's what we typically would do uh, for people that are interested in debottlenecking their productivity. That's what we typically do. We're not just saying, okay, here's the machine. No, here's the machine. Give me all your data, and we'll calculate the return of investment and project how much money or how much volume you're going to be able to increase in your capacity to extend your facility just by utilizing this machine. So, the, summarizing, you can eliminate your drum ovens because you don't need to heat them anymore. So, right there, you have 10 hours less. You can decant at 20,000 centistokes. We still rinse the drums. We still flush the drums on the inside, so we leave no residue. Of course, no matter, even if you tilt the drum and you extract it, you still have some residual quantity. The difference is this. First, we minimize that by tilting the drum and putting the lens at the bottom, but also because we have rings, instead of leaving a small residue of additive, we rinse with base oil. So we inject hot base oil as we go down like a spray. We wash the walls of the drum from the inside, and then we suck and take out the additive. If there's anything remaining in the bottom of a flat drum, is base oil, because essentially we have replaced and extracted the additive, flushing it with base oil. The base oil that is a component of the formula that you're doing. So we have inlets from base oils that are used in the formulation. Anyway, the idea is to go from half hour to 9 minutes in decanting your drums and increase your productivity. That's so there's kilowatt savings, there's time savings, there's increased productivity, which represents a net revenue that we can calculate for a specific application. In general, for people that are not familiar with what ABB Cellier does, well, yes, of course, we do drum decanters, and that's one of the key factors in debottlenecking a plant. We also do batch blenders, we do inline blenders, we do piggable manifolds. The next session on technology and the rate of return is going to be around the best way to manage waste is not to produce waste. So we're going to be talking about the reduce waste generation through the process of pigging the transfer line. We also have control systems as control all these components. They work on an MES configuration, so we don't need to modify your existing hardware. We can run on top of it, controlling these units. Cellier has been doing this for, I think, about 60 years. I'm not that old, so I'm not sure how long it's been, but we are in the process of continuous development of new technology that we're analyzing it as a function of how this may impact in the productivity, not only technology per se, technology as a function of increased productivity. That's why the next session is going to be about manifolds, piggable systems and manifolds. We're manufacturer of robotic arms. ABB is a big manufacturer of robotic, so we'll bring in the new technology into the marketplace and adding robotization of the functions. But that's part of the next session that we're going to be doing. And I mean, 5 minutes left. I don't know if there's any question. Crystal, I hand it back to you.
Yeah, perfect. And thank you, Pablo. So like you mentioned, we're going to go ahead here and take some time for questions now. Just a reminder, be sure to type in your questions that you see the Q&A box on the right of your screen. Send them in there, and then I'll read them out for Pablo. During your presentation, a couple came in. First one is, how long does it take to heat the base oil in the rinse tank?
Well, it all depends on, of course, what temperature, where are you, what's the temperature of your base oils. But let's assume that it's not freezing outside, that you bring something that is, I don't know, 15 to 20 C, and you want to heat it up to at least 45 to 55 C. So it takes about 20 minutes, but you don't have to be waiting for that to happen, because typically there's a setup. You know the batch that you're going to be running. So the first thing you do is load the base oil and start heating it. Then you bring the drums, you align the drums on the conveyor that the ones that you're going to be decanting. The operator typically puts them in the sequence that he wants it per the recipe. The formulation tells you this many drums, but there's a sequence that is also formulated which components go first, and there's a reason for the chemistry of in what sequence they should go into the batch. So he aligns all those and removes the lid on the bunghole and gets them ready. So by the time he's bringing the first one, he's decanting the first drum. By the time he finishes decanting the drum, already 20 minutes have passed, so the basil is already ready and available to rinse by the time he's rinsing the first drum. So on average, it's about 20 minutes, which doesn't mean that you have to be waiting 20 minutes to heat the basil, because usually the setup and the lineup of the batch and bringing all the drums and all that, it can be done in parallel to the heating process.
All right, great. Thank you. We got a question here more on budget. It says, if we were to consider this drum decanting unit for our next CapEx, how much should we budget for?
Well, drum decanters have many different features. How many basils are you going to be using? Are you heating with steam or hot oil? Are you doing it in which degree of automation? Is it integrated to a DCS? Is it standalone? So there are many different features. If you have to budget it, you have to also consider the cash flow of the investment. These machines are anywhere between 8 to 9 months by the time they get to your facility. So you can prorate about probably 400,000 US dollars in 9 months as the investment that you have to do, considering that you will have to have a connection for steam, a power, or hot oil. You will have to have air for the pneumatic parts of the machine. You will have to have an electric drop to for the motors. So considering all that, budget in a 9 month period, uh, about 450,000 US.
Excellent, thank you. Looks like we've answered everyone's questions. I don't have any other ones that have come in. So thank you, Pablo, for your presentation today. And before we close the WebEx event, I just want to also thank our attendees for their participation in today's Tech Talk webinar. I hope that you found it interesting, and I would encourage you to reach out to Pablo if you have any additional questions. And at the close of the event, you'll see a pop-up for a short survey. If you can please answer the 3 questions, that'd be great. Moving forward, it helps us evaluate and reassess for future presentations. So I wish you all a great afternoon, and thanks again.
Thank you all.
Bye.
Bye.